Welcome to the ninth video on compressible fluid flow. My name is Dinesh, Assistant Professor, Department of Mechanical Engineering, and in this video we will be studying about isentropic flow. Now, in the previous video, towards the end, we discussed that the compressible flow based on the driving potential are classified into different simple compressible fluid flows. The first one was the flow in which the properties changes due to change in area, which is also referred to as isentropic flow. So in this video, we will start discussing about isentropic flow in detail. Isentropic flow is a simple compressible flow in which the driving potential is the variation in flow area. As the fluid passes through the duct, the change in fluid properties is because of change in the area. In this, the effect due to friction, heat transfer, mass addition, etc. are absent or are negligible compared to the effect induced by the varying area. This is used to study variable area ducts which are used as nozzles and diffusers. Nozzles and diffusers find wide application in the use of rocket engines, aircraft engines, the design of wind tunnels, and in steam turbines. Now let us look at the important assumptions that are considered for the study of isentropic flow. First, we consider that the flow is a steady flow. That means there is no variation in the properties during the flow with respect to time. So all the transient terms becomes equal to 0. Second, we consider that the flow is one-dimensional. That is, the flow takes place only in one direction, like shown in this figure. It takes place in the direction of positive x-axis. The y-axis, z-axis flow is considered to be 0, and there is no variation in properties in y and z directions. The body forces are considered to be negligible. That helps us to simplify our momentum equation. Working fluid is a perfect gas. Because of this, we can apply all the perfect gas equations into our working fluid. There is no heat transfer between our control volume fluid and the surrounding fluid. That is, the flow is adiabatic flow. Now I told you that the isentropic flow is used to study flow through variable area ducts. That is used as nozzles and diffusers. They are of very short length and the fluid travels at a very high velocity through these ducts. Because of this, the flow process takes place at a faster rate. Hence, we can assume without any error that there is no enough time for the exchange of heat between the system and the surrounding, and hence we can say that the flow is adiabatic. There is no work transfer involved during the flow process. This is a flow of fluid through a variable area duct. There are no rotating elements that would be taking energy from the fluid or will be imparting energy to the fluid. Hence, shaft work remains 0. Frictional effects are negligible. Not the point that it is negligible, not absent. That is, it is a flow through a duct. So there will be skin friction. But as I mentioned earlier, the length of the duct will be comparatively smaller, and because of that, the net viscous effect developed within the duct can be neglected with respect to the changes that is brought in by the change due to area. The variation that frictional effect has on the fluid properties are negligible. There is no mass transfer. In between the control volume, there is no mass of fluid being added or there is no leakage of fluid from the control volume. Hence, we say that the mass transfer during the flow is zero. In the introductory video to compressible fluid flow, we have learned about different conservation laws. It was mentioned that these conservation laws governs a fluid flow process. Here we will obtain the governing equations for an isentropic flow from the conservation laws. We will start with the law of conservation of mass, also known as the continuity equation. We learned that for a steady one-dimensional flow, the mass flow rate in is equal to the mass flow rate out of the control volume. Or we can say that mass flow rate remains constant throughout the flow. We also obtained that mass flow rate is a product of density, area and fluid velocity. Therefore, we can also write rho AC is equal to a constant. So, the law of conservation of mass reduces to this simple form for an isentropic flow. Next, we have the law of conservation of momentum, also known as the momentum equation. Here, we have the sum of external force acting on the control volume equal to the difference of inertia force of fluid in and out of the control volume. In this case, we neglect the body force, the viscous forces are negligible, so we are left with the pressure term and the reaction force that is developed because of variable area. Hence, our momentum equation reduces to the simplest form as shown in the second equation. For law of conservation of energy or the energy equation, we start from steady flow energy equation, which is the simplified form of energy equation for a steady one-dimensional flow. Here, for an isentropic flow, the work transfer and heat transfer term reduces to zero. The change in energy due to elevation is also zero. Hence, our steady flow energy equation reduces as H1 plus C1 square divided by 2 is equal to H2 plus C2 square divided by 2. Or we can write H plus C square 2 is equal to a constant, which means the sum of enthalpy and kinetic energy remains constant throughout the fluid flow. If you refer back to the adiabatic energy equation, we see that at a particular point in fluid, the sum of enthalpy and kinetic energy gives us the stagnation enthalpy. Combining these two results, we can say that stagnation enthalpy H0 is equal to a constant for an isentropic flow. The second law of thermodynamics reduces to the form that entropy is equal to a constant, since it is an reversible process. So these gives us the governing equations for an isentropic flow. Here let me point out the importance of assumptions and governing equation in the study of a flow process. When we are going to apply our knowledge in order to study a variable area duct, we have to be sure that the study that we are going to carry out are in agreement with the assumptions. We see that all the governing equations has been simplified and reduced to the following forms because of these assumptions. If the assumptions are valid, only then the conservation laws holds true with these equations. So it is very important that we understand what are the assumptions and how the governing equations has been achieved by applying these assumptions. And when we are doing our study in the real life, we have to make sure that these assumptions hold true. Now let us see how we can represent an isentropic flow in a thermodynamic state coordinate system. For this, consider a flow as shown in figure. The arrows indicates the direction of flow. Consider 2 points A and B for plotting it in the state coordinate system. 0A and 0B represents the corresponding stagnation conditions. We have pressure sensors and temperature sensors to measure static and stagnation pressures and temperatures at A and B. Note that point A is at a position where the cross-section area is reduced. So the fluid velocity will be higher at point A compared to that at point B. So basically there is an reduction in pressure as the flow passes from point A to point B. Keeping this in mind, let us move on to the HS diagram. Let us start with plotting the point A. Here we get the corresponding enthalpy as static enthalpy of point A, that is represented as HA. This is the corresponding entropy, that is represented as SA. The constant pressure line passing through A gives us the static pressure. Now as the fluid progresses through the duct from A to B, there is a reduction in kinetic energy. When the reduction is there in kinetic energy, there is an increase in static enthalpy. So the point B will be lying above the point A because this is having lower kinetic energy and higher enthalpy. And since it is an isentropic flow, it will be connected by a vertical line. So point B lies vertically above point A. So by moving vertically above, we reach at point B. We get the corresponding static enthalpy HB and the corresponding entropy SB, which is equal to SA since it is an isentropic flow. The constant pressure line passing through B gives us the static pressure PB. Now, from the governing equation, we know that the stagnation enthalpy remains constant for an isentropic flow. So, at point A and at point B, the stagnation enthalpy is constant, which is represented by the point 0 in HS diagram. So this represents the stagnation enthalpy, that is H0A is equal to H0B. The constant pressure line passes through this point, which gives the stagnation pressure at point 0. And we see that the stagnation pressure also remains the same during an isentropic flow. Now let us come back and see how the kinetic energy variation is depicted in an HS diagram. So up to the height point A, this represents the static enthalpy HA. From A to 0, it is the kinetic energy possessed by the fluid at point A, that is Ca square by 2. To the point B, we have the static enthalpy HB, and from B to 0 is the kinetic energy possessed by the fluid at point B. Since it is moving from a restricted area to a larger area, the kinetic energy will be reduced, and that reduction will be reflected as increase in enthalpy. So because of this, the static enthalpy at B is larger than the static enthalpy at A, and the kinetic energy at A is greater than kinetic energy at B. The region up to 0 represents the total enthalpy. Now we can see that the fluid with higher velocity lies away from the stagnation condition, and the fluid with lower kinetic energy lies closer to the stagnation condition. In an HS diagram, as we move towards the positive y-axis, we see that the pressure value goes on increasing. Therefore, we can say that the pressure PB is greater than PA. Therefore, when the fluid moved from point A to point B, it experienced a certain level of compression, and its pressure increased to a higher value represented by PB. The point to be noted here is that this compression was obtained not by supplying any external work. It was because of the virtue of area change. All that happened was, as the flow progressed, one form of energy got converted to another form. Here, the kinetic energy got converted to the internal energy and pressure energy of the fluid, the sum of which is represented as enthalpy. So if it is a isentropic flow with increase in pressure, it will be proceeding in the positive y direction, and if it is an isentropic flow with expansion, that is reduction in pressure, then it will be moving vertically into the negative y direction. Now let us compare an isentropic flow with an adiabatic flow. An isentropic process is reversible adiabatic process. If we can make an adiabatic process reversible, that is, maintain the entropy to be the same throughout the flow, then we can obtain an isentropic process. And we know that reversible processes are highly idealized processes. Hence, we can say isentropic flow is an ideal process, whereas adiabatic flow is an actual process. Entropy remains constant during an isentropic flow, whereas there is an increase in entropy during adiabatic flow. The entropy is related to the available energy of the working fluid. When there is an increase in entropy, there is loss of available energy. Hence, the available energy remains intact for an isentropic flow, whereas it reduces during an adiabatic flow. Now let us see how we can represent isentropic and adiabatic flow in an HS diagram. We have shown here an expansion process as well as a compression process. Let us focus on the expansion process. The expansion takes place between two constant pressure lines. One represents the starting point and two represents the end point. If it is an isentropic process, the flow proceeds from 1 to 2s, that is vertically downward. In this case, the entropy remains constant. Whereas if it is an adiabatic flow, from the moment it starts moving away from point 1, it deviates from the ideal isentropic flow because of increase in entropy, and it reaches the point 2a. So process 1 to 2s represents an isentropic flow and 1 to 2a represents an adiabatic flow. We see that the change in enthalpy for isentropic process is greater than the change in enthalpy for adiabatic process. This difference results in loss of available energy and is manifested as increase in entropy of the working fluid.